Now let's move on to electrostatics. This is really the first time you'll get to encounter electric charge, and then we're going to first examine what a charge is, and then move on to how we can leverage its properties to calculate electric force. But the first thing is, even though we're learning about electricity and magnetism in this course, we should at the very end be able to apply E&M to life and medical physics. So why is it even important to us? E&M is critical to our understanding of the universe. So there are so many different things that we encounter in our everyday life that depends on the fundamentals and foundations of electricity and magnetism. So these would be the computers we use to study and do research on, play video games with, calculators, cars, there's television, mobile phones, radio waves, and signals. But not just that, we're leaning towards biophysics and medical physics. So there are processes within the human body, such as neuronal signaling and muscle contraction from electrical signals that rely heavily on the foundations of electricity. So understanding all of these concepts, both within the body and outside in the environment, can help us create and understand applications to biology and medicine. A few of the things that we will focus on in this course at the very end, after we've learned all about E&M, is MRI imaging, so magnetic resonance imaging. And this is very crucial in diagnostics, for especially different diseases. You can also have RF, radio frequency applications in oncology, physiotherapy, tumor therapy, and so on and so forth. And so these are things that we will touch on throughout the whole course. But it's really rare that one application that we use for life and medical physics just relies on electricity or just relies on magnetism. This field is electromagnetism, essentially. So we do have to understand both in order to grasp how these applications work, which is why the focus of this course really is about making sure you understand the concepts, be able to do a little bit of the math, and then, of course, understand the applications and how to use them. So the first half, a little bit less than half of the course, will be about electricity. Then the next part will be about magnetism. So this whole chapter will just be about electricity, specifically forces and fields. So the big picture that we're going to go through in this chapter is the electric charge. Once we understand the electric charge, we can understand the electric force. And from the electric force, we understand that we can generate or at least see an electric field from these electric charges. And the electric field would be the force that a charge would experience if we placed it near other charges. Now, once we have the electric field, we can figure out how strong an electric field is by looking at how many electric field lines penetrate a specific surface. And the way to measure that would be through electric flux. And once we have a good foundation in all four of these, we can move on to Gauss's law, which relates electric field to the charge itself. So all of this together will give us a really good foundation to start our journey into electricity. So all the building blocks of matter possess what we call a charge. So this is something that you should know of already. It allows us to look at the quantization and conservation of these charges. And from this, we can analyze the force between two charges using Coulomb's law. So let's start with electrostatics. Electrostatics really is the study of electricity by considering systems of charges at rest. So they're not moving. Where can we see this? Just a really brief history. A piece of amber was rubbed against cloth and it attracted straw. So that is what the Greeks noticed way back in around 600 BC. And they called amber itself electricus. And that's where the electricity the word electricity came from. We can also see this from electrostatic shock when you get out of a car. rubbing a balloon on wool sticks, on wool will stick to either the wall or hair. These are all things that we have seen throughout history and throughout our lives that are based in electrostatics. So let's take a look at what happens when we rub two objects together. This is what the Greeks had noticed back in the day, and so we want to at least have a scientific explanation for what they observed here. So when we rub two objects together, small amounts of charges, in other words, electrons, are transferred from one material to another, and this is called the Triboelectric effect. Now, different materials that we hold will have different tendencies to give or take electrons, and the Triboelectric series that you see here gives us the tendency of a material to donate electrons, or essentially to hold a positive charge. So if we rub amber with fur, what the Greeks saw was that even though fur isn't really on the chart here, it's actually quite high up in the Triboelectric series, which means it prefers to acquire a positive charge. And for materials that want to acquire a positive charge, they like to donate electrons. So when we rub amber with fur, the electrons are going to move from the fur to the amber, making the amber more negatively charged because it has more electrons, and making the fur more positively charged. So that answers question 1. Now, question 2 is based off of this entirely. What about rubbing a glass rod with silk? So let's take a look here. A glass rod is up here and silk is down here. So glass has a higher tendency to acquire a positive charge, which means it's going to donate electrons to silk. That's going to make the silk negatively charged and the glass rod positively charged. So being able to understand the Triboelectric series can help you determine what object will end up with a positive or negative charge. Now, let's start a discussion of electric charge by looking at an atom. So a modern day picture of the atom is presented here, right here, where the central nucleus is made up of neutrons and protons, and you have, of course, the protons are positively charged and the neutrons are neutral. They are then surrounded by a cloud of negatively charged electrons. So both protons and electrons have the same magnitude of charge. It's approximately 1.6 times 10 to the negative 19 coulombs. The only difference is whether it's positive or negative. So instead of saying 1.6 times 10 to the negative 19 coulombs, we call this E, the magnitude. And E is called the elementary charge. So for neutrons, we have a charge of 0, but for electrons and protons, we have a charge of negative E and positive E, respectively. Now, here are also the values of the mass for protons and neutrons, the same, and electrons being this. Now, these are not values that you have to memorize, just to understand. Next, the electric charge is considered a conserved quantity. So this is something we'll discuss on this slide. But the other important thing is that later on in the next chapters, we're going to talk about conductors and insulators. So, or dielectrics. Conductors are those that allow charges to freely migrate throughout the material, and dielectrics are those that don't allow charges or electrons to flow easily through them. But no matter how much the charges move around, electric charge is a conserved quantity, so that means it cannot be destroyed and it cannot be created. It's rather just going to be redistributed to have different particles or have localized areas with varying charges. So this is something that you should remember as a concept. The conservation of electric charge means that the net electric charge in an isolated system must remain constant. So this will be very handy when it comes to discussing conductors, and especially conductors where charges are free to move around. So now that we understand what a charge is and we know what kind of positive or negative charge it holds, either an electron or a proton, we can then take a look at attractive and repulsive forces, which are governed by the electrostatic force. So let's take a look at Coulomb's law in detail. Let's say that we have two charges. We have, capital Q and little q, and we're just going to assume that these two are point charges. We're going to assume that a point charge is a charge with a radius that's close to 0, so it looks like a singular point. So whether there's attractive or repulsive forces doesn't matter at the moment, but we do know that there's going to be some force from the left charge acting on the right charge and vice versa. So the way we take a look at this is over here, the blue charge is going to affect the red charge, and it's going to point in this direction, for example. So there's going to be a force from little q on big Q, and that's what this red one represents. Now the blue arrow, or the blue text over here, represents the effect of charge capital Q on little q. So we have F capital Q Q over here. Now, looking at the big Q in red, it's going to experience a force from the little q, and we're going to define them using these following equations. So you can see them here. Over here in blue, the unit vector is pointing in the direction of, so we have R capital Q to Q. It's going to point from here to here because the force is acting from this point towards the little q on the right. So that's why we have this arrow over here representing the direction of the force. The next thing I want to talk about would be the units. In SI units, both charges are defined in coulombs, or C. Distance R is going to be in meters, and the force is going to be in newtons. K is a universal constant called Coulomb's constant. It's 1 over 4 pi epsilon naught, and it is equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. So once again, these two constants are not things that you have to memorize. Obviously, the more you use them, the more it'll just be burnt into you. But in terms of doing calculations for this course, all you would have to end up with would be not a numerical value, but rather a variable solution that has k or epsilon naught in it. So I'm not too worried about memorizing constants in this course. Now you may notice that k is also equal to 1 over 4 pi epsilon naught. The epsilon naught is called the permittivity of free space. I won't be going through what this means. If you're interested, you can talk to me about it after. But whether you use k or the epsilon naught version, it will become very clear which one to use if you have a form or if you have variables that cancel each other out. It depends on the situation. Sometimes you end up with a question that has a 4 pi in it, and if you want to simplify your solution, then you may want to use this form. Otherwise, you can always keep it to k. Last but not least, we do want to talk about, let's get that diagram here. We do want to talk about what happens if we're looking at more than just two charges. Let's say that there are three charges like in this diagram with Q1, Q2, and Q3. So you have these three charges over here. Now, the principle of superposition says that when we're talking about electrostatic forces, if we want to find the force on one of these objects, it's not just going to come from one charge, it's going to come from a combination of charges. So the total force or the net force felt by, let's say, Q3 will come from the electrostatic force between Q2 and Q3, as well as the electrostatic force from Q1 and Q3. So looking at these two, just because we know they're whether they're positive or negative, I have Q3 over here and it's a positive charge, which means if I have another positive charge here, like charges repel, and so there's going to be a force from 1 on 3 going towards the right. So that makes sense. Now you have a negative charge in Q2. It's going to attract the positive charge Q3. So therefore you have a force or a pulling force from 2 onto 3. Now these two added together will give you a net force pointing in this direction. So you can either use tail-to-tail addition, so F1 to 3 over here and then F2 to 3 over here, or you can use another method of adding up the vectors, but you should be able to calculate the net force from different charges. So all of electricity and magnetism is essentially based on this principle, and although there is no reason it should work, every experiment that has been performed on this topic has verified the principle of superposition, and the entire field of E&M is rooted in this principle. So next we're going to go through a practice problem to try and calculate the force of 3-point charges. So the first problem we want to go through is how to calculate the force of 3-point charges. So the first thing is we need to understand the problem. It says consider 3-point charges on the XY plane. There's Q1, Q2, Q3. It tells us the charge. It tells us the exact coordinates where the charge is located. Once we have that drawn out, we are supposed to find the magnitude and the direction of the force acting on Q3 if the distances are measured in the SI system of units. So first step is to draw everything out. And so it says right here, the first location of Q1 was 0, 2. I'm just going to write that down. This was 0, 2. Then you had a second location, 0, -1. Like that. Then you had the third location, which was 1, 2, 3, 0. So now that you have all 3 locations, we want to figure out the forces acting on each one. And so instead of drawing this all out, I do have... Okay. So looking at this, we want to comment on this next diagram. We do have the 3 charges, and now it's really important to know what forces are acting on which object. So we are looking at the total net force that Q3 over here experiences. So I'll just say we want to find, the net force acting on Q3. So I want to take a look at Q1 acting on Q3 first. The fact that Q1 is acting on Q3 means that my position vector must go from Q1 to Q3. However, because it is a negative charge where Q1 is equal to, just don't forget, Q1 is equal to -3 microcoulombs. So we now have the force of 1 on 3 being an attractive force going towards Q1. For Q2, we know that Q2 is going to be plus 7 microcoulombs. So in that case, we also have the position vector going from 2 to 3, but because it's a repulsive force, the arrow for the force acting from 2 to 3 must go towards the right, pushing the Q3 away. So purple is representative of the force that Q3 feels from Q2. So once we have this, it's important for us to calculate the net force acting on the Q3. I'm just going to take a look here. So the first thing is we want to we want to draw out the components of each of these force vectors and then add up all the components to get the final vector. So what we can do is take a look at the green vector F13 pointing towards the left, and we take a look at the purple vector F23 pointing towards the right. And we create the horizontal and vertical components for each one. Now let's see if I've labeled this correctly. I want to label this as F13x to say it's the x component of the F13 vector. I want to label this as F13y as the y component of the F13 vector. Similarly, I do the same thing for F23 here and here. Now that we have this, we really do have to start calculating some values. So we're going to start with that next. I also want to label this to show that this is an attractive force. And this is a repulsive force. Oops. So looking at this, I really should break this up into two separate triangles so that I can at least figure out something to do with this so that I can proceed with calculating the net force. I have to find the magnitude of the component, so that is the next step. So I'll just keep that up there so I can do some work here. So let's start off with F13. We know that F13 is equal to K Q1 Q3 divided by, now we have to have some sort of distance between Q1 and Q3, and we labeled that as R13 squared, and then the unit vector is R13 because that's the direction it's in. Now we have to break this apart into its x and y components. So I know that for one, if we take a look at the x component, we have F13x is equal to KQ1 Q3 divided by R13 squared, but I have to change the component or the unit vector to 13x unit vector. And this is where we have to do a little bit more analysis. I'm now going to go back up and we're going to try and determine what this unit vector is going to be. So right now I take a look at this and I really don't have any numbers to work with. So the next thing I have to do is try and give it some numbers. And so the first thing I see is that I should probably figure out the distance between each of these points. I know that over here it's 0 for the origin, and I do know that between here and here we have 3. So I'm going to draw another diagram of this. So this is where Q3 is. This is the origin. And this is where Q1 is. This distance between 0 and Q3, because Q3 is at 3, 0, I know that the distance is 3 over here. I know that Q1 has a distance of 2 above the origin. And I know that this angle is called theta 1. So between all of this, I also know that if I have a distance between Q1 and Q3, it's going to be R13 is equal to the square root. So a squared plus b squared equals c squared. For a right angle triangle, that would be 3 squared plus 2 squared, or 9 plus 4, which is 13. So now I have this. If I do want to break it down into its component form for a unit vector, so that would be this one, going from here to here. That would be the R13. R13 unit vector is going to be equal to the actual vector R13 divided by the magnitude of R13. So the vector R13 is going to be, we'll have to take a look at it, but the way we create this vector from Q1 to Q3 is going towards the right by 3 and going down by 2. So that tells me that this is going to be given by 3 minus 2. And we are going to divide by the magnitude, which is the square root of 13. So from this is a component analysis of the vector. I know R13x is going to be 3 over the square root of 13. And I know R13y is going to be equal to minus 2 over the square root of 13. So this is how we would do the analysis so that we can move forward with the question below. I'm going to go down. Now that we have R13x over here, I should be able to proceed. And that means I should be able to calculate this to be equal to 9 times 10 to the 9. We just make sure it's the correct units, Newton meter squared per Coulomb squared, minus 3 times 10 to the negative 6 coulombs for Q1. And then for Q2, we have 9 times 10 to the negative 6 coulombs divided by R13 squared. We know R13 was the square root of 13. So now this is just that squared, multiplied by R13x, which we just calculated it to be 3 over the square root of 13 in the x hat direction. So that actually gives us approximately negative 0.0156 newtons in the x hat direction. Now we want to figure out what happens in the y direction. So we have F13y. And it's a similar situation. We now have K, Q1, Q3 divided by R13 squared, but we have R13y. And this is equal to, if you do the math, it's going to be 0.0104 newtons in the y hat direction. So you do this for the next two. I'm going to start with This one, we now should probably calculate f of 2 on 3. So f of 2 on 3, that would be the effect of the second charge on the third charge. I'm going to say that it will be k q2 q3 divided by r23 squared, r23 hat. And once again, we're going to have to do our x and y analysis. For our x analysis, we have f 23x, which is equal to q2 q3 divided by r23 squared times r23x. So now that we've hit this, we now have to figure out what r23x is. So we go back up. And we take a look at r23, this one. So we know that we have this. We know we're taking a look at this triangle right here. I know this is going to be theta 2, the same as this angle right here. I know that this is 3. I know that this is 1. And that means I know this. The magnitude of r23 is going to be the square root of 3 squared plus 1 squared, which is 10. So if I'm trying to figure out what r23 is as a unit vector and figuring out the x and y components, I have r23 divided by the magnitude of r23, which is equal to, let's keep this in mind, we want to create the vector for r23, and r23 is you go towards the right by 3 and you go up 1. So right 3, up 1. Divided by the square root of 10. So that tells me that I have r23x being equal to 3 over the square root of 10. And then r23y being equal to 1 over the square root of 10. So now I can use this and go back down. And finish my calculation here. I essentially have 9 times 10 to the 9. Q2 is 7 times 10 to the negative 6. I know Q3 is 9 times 10 to the negative 6. And it's all divided by r squared. So that r is the square root of 10 squared. But this is r23x, and we determined that it was this in the x direction. So the answer is approximately 0.0538 newtons in the x hat direction. And we move on to the next one. We have F 23y, which we can simply put as F23 multiplied by the y component of the unit vector, which is equal to 9 times 10 to the 9, 7 times 10 to the negative 6, 9 times 10 to the negative 6. Just make sure your units are correct. Squared is 1 over the square root of 10, because that is the y component, and you have y And so you should be able to get 0.0179 newtons in the y-hat direction. Okay, so now that you have all this, we should really move on to figure out how to combine all the components to find F3. So that would be the next step. We're going to take all of this and merge it together in the next slide. So because we were able to figure out the X component contributions for each of the forces and also the Y components, we can simply add them up separately and then combine them together at the end. So what we want to do is figure out F (3x), which is equal to F 13x plus F 23x. And that is going to give us F 3x with some sort of direction. We have negative 0.0156 newtons plus 0.0538 newtons. And so that is equal to 0.0382 newtons in the x-hat direction. Then you also have F3y, which is equal to F13y plus F23y. So we're adding up the individual y components for each one that we just calculated. And if we keep to the positive and negative, then we can actually figure out the direction as well. So we have 0.0104 newtons plus 0.0179 newtons. And that's equal to 0.0283 newtons in the y-hat direction. Now with both of these, we can figure out F3, but the only way to figure out F3 is if we first draw out these vectors. So together you have, starting from this point, you have, F3x, and then you have F3y. And the final vector is going to be this one in red. With a certain angle theta. So in order to determine this, we know we can use Pythagoras again. So F3 is simply going to be the square root of F3x squared plus F3y squared. And that is going to give us 0.0475 newtons. Now for the angle, you can say tangent. The tangent of theta is equal to opposite over adjacent, which is equal to F3y over F3x. So that means theta is going to be equal to the arctan of F3y over F3x. And theta is equal to 36.5 degrees. So altogether, you can say, therefore, F3, or the net force acting on 3, is equal to 0.0475 newtons. And you can have 36.5 degrees above the horizontal. And that would be your answer for this question.